This is part B, question 13 of Seoul National University's mathematics aptitude exam that was held in 2024 February 4th. And this states that of the function that is defined as such from the domain of 0 to pi over 4 inclusive, find the length of the graph itself. So by saying the length, what this question wants us to find is, for example, if the function looks like this length itself, how long is this? The reason I chose this question is because this is a really good practice for students who are studying calculus for the IB AHL mathematics. And this isn't in the syllabus. However, it had occurred in some instances of paper 3 questions. So this is a really good exercise to really seek understanding of further calculus lessons. So firstly, let's assume this is f of x, because I don't know what f of x looks like, but let's just assume that this is what f of x looks like. Then I want to find the length. So how would we approach this? How would we approach this question? Well, the most intuitive explanation would be if we zoom right in, and then we can assume that some point is a triangle where the displacement of the x is really small amount of dx, and the displacement of y is a really small amount dy. If the dx and dy are very small, but is finitely small, it's not infinitesimal, by the way, then we could assume that this length of the graph that is parted by dy and dx is a straight line, right? This is what we do in differential calculus when we learn that the first principle differentiation is where limit as h approaches to 0 of f of x plus h minus f of x all divided by h. We're assuming that these changes are really small so that we can assume it as to be a triangle, I guess. So that would be 90 degrees. Then that blue length, let's call that L. Well, L at some point, any point of f of x would be root of dx squared plus dy squared, because this is the Pythagorean theorem. We're assuming that dx, dy, and L, or more specifically, L is the hypotenuse of this right-angled triangle. Well, I'm going to rewrite this. I'm going to multiply and divide by the whole thing by dx. dx divided by dx. So this is basically the same thing because the dx cancels out to become 1. Therefore, I can rewrite this as dx squared plus dy squared all over, dx was outside the root. However, if we put it inside the root, we have to square it, obviously. So that would be dx all squared, and dx outside the root. So we can simplify this to be dx over dx all squared plus dy over dx all squared of dx outside the root. And we know that the rate of change of x divided by the rate of change of x, even if the rate of change is really finitely small, that will just cure to as the limit for 1. So that would be root 1 plus dy over dx squared dx equals some length L. Now we want to find the sum of all L's throughout x, and we know that in order to do that we just integrate. So we can say that length subtotal, which is the answer we want to find, the length of the function, is equal to the integral from, it's defined from 0 to pi over 4. It's from 0 to pi over 4 of root 1 plus dy over dx squared dx, because we are adding all of the small lengths together in order to get the final total length of the function itself. So what is dy over dx squared? Well, we have our original function, which is defined as a indefinite integral from 0 to x of root sec to the 8 t plus minus 1 dt. So let's then what we can do is, if we integrate f of x, let's call this part, I'll paint it in red actually. I'll call this part g of x, just for communication reasons, and I will call and let the integral, the indefinite integral of gx dx, be capital G of x, because that makes sense. This notation of capital letters and small letters representing the derivative and integral is mostly used in things like fundamental theorems of calculus. So we can rewrite fx as big G of x minus big G of 0, because that is the definition of what an integral is by the fundamental theorem of calculus. It's this, whatever this integrated is, you plug in x and you subtract it by what you plug in by 0. So that's fx. There is a reason why I want to do this, because we want to find dy dx in our original function, right? So dy dx, or we can just call that y, I guess, then dy of dx equals big G prime x minus big G prime 0. But G of 0 is just a number, right? So if we differentiate that, that just becomes 0. So we can ignore that. But what is G prime x? Well, that's just small g of x from our definition, because we let gx and then we let the integral of gx be capital Gx, right? So our dy dx is actually just the inside of that integral, but not with the variable t, but with the variable x. So our dy dx is just sec 8 of x minus 1. So now what? So now we know that the answer we want to find is the integral of 0 to pi over 4 of root 1 plus that squared. So the root cancels out, right? 1 plus sec to the 8x minus 1, right? dx. And that works, and that is precisely why the question gave the inside function as a root, because they wanted us to square it, I guess. The 1 and the minus 1 cancels out, and the root cancels out with the sec 8, so we get a sec to the 4, right? Because it's half times 8. So we get our final calculation to be 0, integral from 0 to pi over 4 of sec to the 4th power of x dx. And I'll call that, I don't know, capital L. Let's say that. Now, all we have to do now is integrate sec to the 4. But it's not that easy here. And it's really not easy to see it if you do it firsthand, because we cannot substitute u equals sec x, because that won't cancel out with the du dx. So what we do is we use our Pythagorean theorem. The Pythagorean identity, let's say. We know that cosine squared x plus sine squared x equals 1, always, because it's the definition of a unit circle as a polar form, right? So if we divide everything by sine squared x, let's say, by sine squared x, by sine squared x, by sine squared x, then we can say that, sorry, that's cosec, right? I will divide everything by cosine squared x, because I think that would make our life much easier. Cosine squared x, 1 divided by cosine squared x. That, the left-hand side, because 1 plus tan squared x equals 1 over cosine squared x, which is defined as sec squared x. See where we're going now? So, so we can rewrite this as 0, as the integral of 0 to pi over 4 of 1 plus tan squared of x times sec squared of x, right? Now, those of you who are more familiar with this might see, because when we differentiate tan x, we get sec squared x. So that makes our life easier. So here we can say let u equals tangent of x. Then we get du equals sec squared of x dx, right? So we get integral from 0 to, from x equals 0 to x equals pi over 4 of, because tangent of x is u, we can call this 1 plus u squared times sec squared of x times dx, which is just du divided by sec squared of x, right? Because it cancels out. Now, and I'll say when x equals pi over 4, because u equals tangent of x, tangent of pi over 4 is 1, because sine pi over 4 is root 2 over 2, cosine of pi over 4 is root 2 over 2 as well, therefore, and tangent of 0 is 0. So we can change the boundaries of the definite integral from 0, u equals 0 to u equals 1, of 1 plus u squared, sec squared cancels out, du. Now we know how to do this one. So this is just u plus u cubed over 3 from 0 to 1, which is 1 plus 1 over 3, which is 4 over 3. Therefore, we can say that the length of this function, I don't know how it looks like, but should end up as 4 over 3 units. Thank you very much.